Hello, everyone. So welcome to the first session of the second day. So our first speaker is Biaoshuai, and he will speak on existence of truthful fair cake cutting mechanisms.
Very good. Hi, thank you. Good morning, everyone. I'm Biaoshuai Tao from Shanghai Jiaotong University. I'm going to present my work on existence of truthful fair cake cutting mechanisms. So the cake cutting problem is a classical resource allocation problem, which studies how to divide the divisible heterogeneous good, that is cake, fairly among the agents. So the typical divisible resources includes the cake, time, line, computational resources, and so on. And we are talking about heterogeneous resources, which means different agents may have different preferences on different parts of the cake. And we study two typical fairness notion, envy freeness, which says that no agent should envy the allocation of any other agent.
Sorry, Tao, I'm sorry to interrupt you. Can you put your slides in full screen mode? We see your slides like with all the thumbnails on the left and everything.
Yes, if you could do enter slideshow mode. That would be good. If you click on
is everything good now? I'm already in the full screen.
Click on the slideshow tab up at the top.
Slideshow on the top.
Yes.
Hang
on.
We don't see your slides anymore.
Yeah. So share your screen.
Yeah.
Go. Pull on.
Oh, sorry. Actually, sharing. So sorry. Let me do it again. Like this.
Yeah. What you do? Go to.
No.
There you go. Bada boom.
Yeah. Okay. Yeah. So
like this.
Do you want to start over for the recording's sake?
Okay.
Do you want to start over?
Should I just continue?
It's your choice. You can go from here if you need to. It's fine.
Okay. Yeah. Okay. Sorry. So I'm just going to continue. Now, I just mentioned about the fairness, and there are two typical types of fairness notion that I studied extensively in the previous literature. The envy freeness says that no agent should envy the allocation of any other agent. And proportional says that each agent receives at least his or her average share. And there are many typical applications, like the division of Berlin in the Potsdam Conference after the World War II, and with special auctions and allocation of computational resources, and some other example not drawn here, like scheduling a conference room, booking the time, or bidding for some advertisement slots, and so on. And here's a mathematical model. So the cake is typically modeled as an interval from 0 to 1, and it is allocated to n agents. And allocation is just a partition of the interval 0 to 1. And to model the heterogeneity in the preferences of agents, we assign each agent a value density function, which is the Fi that maps to an interval from 0 to 1 to a real number, a non-negative real number. And for example, if we want to evaluate agent i's valuation on a specific subset S, then you take the Riemann integral of this function over S. And the mechanism is defined as that takes the n-value density function as input and then output an allocations. And in this work, as is common in the, for example, social choice literature, we assume the mechanism, the rules is deterministic. And with this definition, we can formally define what we mean by envy freeness and proportionality, which based envy freeness means Vi of Ai should be no less than Vi of Aj for any pair of agents A and I and J. And proportionality is Vi of Ai should be at least 1 over n, where n is the total number of agents, 1 over n times Vi of the entire cake. In the computer scientist point of view, there's a problem when we come to the representation of Fi. How can we represent arbitrary real function succinctly? Traditionally, there are two different approaches to handle this issue. The first one, we adopt the direct variation, which is what I defined previously. Just take the n function as input and output, but we make some special assumptions on the value density function. A typical one would be that fi is piecewise constant, which means that the k can be partitioned into many intervals, such that fi is a constant on each of these intervals. This assumption is natural in many applications. Moreover, piecewise constant function can approximate most of the most real, arbitrary real functions within any good positions. And the other approach is the so-called Robinson-Webb query model. Instead of asking agent to directly tell the mechanism what the value density function is, the mechanism communicates with the agent with the two types of the queries. The ever queries ask name an interval x and y and ask the agent I to provide his value on this interval. And the cut query gives a left endpoint x and a value alpha and ask agent for right endpoint y such that the interval x and y, x to y was exactly alpha. So in this work, I'm going to take the first approach. And when it comes to the practice, when we're trying to deploy some cake cutting algorithms, a natural issue is that agent may decide to lie and misreport their variation if this is beneficial. So this motivates the study of the cake cutting problem in a game theoretical point of view. So a truthful mechanism is a mechanism under which truthful reporting is a dominant strategy. And the natural question here would be that, so suppose if we want to insist on some fairness notion like envy freeness or proportionality, does there exist a cake cutting mechanism that not only is fair, but also is truthful? So here, the big picture is that I'd like to have a mechanism that satisfies both fairness and truthfulness. And a natural question is that, does such kind of mechanism exist? Is fairness actually compatible with truthfulness? So to answer these questions, as I mentioned earlier, we have two different settings. One is direct variation, but we assume fi is piecewise constant. But the other one is the Robinson-Webb query model. And when it comes to the game theoretical settings, these two models are actually quite different. So the first one, in the direct variation, this is just a one-round game. All the agents move simultaneously. They submit their functions simultaneously, and the mechanism make an output. And naturally, for the Robinson-Webb query model, since this model includes queries, so in this model, normally agents have more room for manipulations. And actually, this is we can achieve a strong impossibility result under the second model, the Robinson-Webb query model. In 2013, Kurokawa et al. Shows that there is no truthful and envy-free mechanism with a bounded number of queries, which basically means that if you want truthful and envy-freeness at the same time, then the mechanism may not even stop. And Bretney and Madison in 2015 proved the theorem that's Gibbs-Sasavit impossibility theorem styled. They show that for any truthful mechanism, under some mild technical assumption, there exists an agent who will just receive a zero value. And let's come to the direct variations. So this slide gives some existing result if the value density function is piecewise uniform, and the piecewise uniform function is an even more special case for the piecewise constant function where the value of fi can be either 0 or 1. We can have some nice positive results under this setting. So Chen et al. In 2010 shows that under the piecewise uniform variations, direct variation model, a truthful and envy-free mechanism always exists with a very mild technical free disposal assumptions. And actually, Chen's work is the first work that proposed this propose a problem of truthful and envy-free existence of truthful envy-free mechanisms. And later, in 2012, Maya and Nissan did some characterization of truthful envy-free mechanisms, and they show that the Chen et al.'s mechanisms is kind of unique in some sense. And in 2015, Li et al. Shows that Chen's mechanism also works under setting with externalities. And Bei et al. In 2020 provides a different truthful envy-free mechanism that can get rid of the free disposal assumptions. So basically, as you can see, most of we can achieve some positive results in the piecewise uniform settings, and the fairness is actually, we can say, it's mostly compatible here with the truthfulness. For the piecewise constant value density functions, most of the results are negative, and so due to the time limit, I'm going to skip all this. But what I want to say is that in this work, there are some impossibility results, but all of them based on some additional assumptions. They show that the truthful and fairness are not compatible under some additional assumptions. But the problem itself, does there exist a truthful and proportional K-cutting mechanism, is still open. And in this work, I'm going to resolve it in an active way. I'm going to show that there does not exist a truthful and proportional mechanism. Here I'm going to give some very high-level ideas on the proofs. Suppose such a mechanism M exists, then I'm going to construct a sequence of K-cutting instances and show that truthfulness and proportionality cannot be both satisfied on all of these constructed instances. So let's take a look at the first instance. We have two value density functions, F1 and F2. They are both like uniform on 0 and 1. So here, just to guarantee proportionality, we have to produce an allocation x1, x2, such that the length of x1 and length of x2 is just 0.5. If this is not the case, then the allocation is not proportional. And without loss of generality, in the picture on the left-hand side, I'm going to just assume x1 is from 0 to 0.1, and x2 is from 0.1 to 1. So let's consider the second instance. F1 is still uniform as in the previous case. F2, the value density function is that its value is epsilon on x1, where x1 is defined in the first, is the output of the first instance, and its value is 1 when x is in x2. So we can argue that under this instance, the only possible allocation is still to allocate agent 1 x1 and agent 2 x2. This is because, firstly, agent 2 should receive a length of at the most 0.5. If agent 2 receive a length of more than 0.5, then in the first instance, agent 2 would lie and say that the valuation function is actually what it is in the second instance. Subject to that, agent 2 can receive a length of at most 0.5. The maximum value he can receive is to receive the entire x2, where she has most value on. And on the other hand, agent 2 should have received x2. Otherwise, agent 2 would lie and say that his value density function is just uniform, which goes back to instance 1 and will receive x2. So the truthfulness as well as the proportionality ensures that under this instance F2, the only possible allocation is still x1 and x2. So so we can construct a third instance like this. I'm going to skip the analysis, which is a little bit more complicated. But with this type of analysis, we can show that under these instances, under F3, the only possible allocation is to allocate x1 and x2 uniformly to both agents. And the remaining part of the proof involve a lot of complicated details. But basically, I construct 6 instances, and the arrow here is like implications. And the previous allocation result of the instances will imply the allocation of some late construct instances. And at the end of the day, we can reach a part where we have a 6th instance, F6, where there's no allocation that can satisfy both fairness and proportionality. So this gives a rough idea of the proof. So I'm going to use 1 or 2 minutes to briefly talk about some possible way to circumventing the impossibility results. So there's 2 natural directions. One is to relax the dominant strategy truthfulness, and one is to relax the fairness. So dominant strategy truthfulness can be relaxed, and there's a common weaker notion than dominant strategy truthfulness is to require the truth telling as a Nash equilibrium. Unfortunately, in the context of cake cutting, these 2 notions are actually equivalent. You can think about this. I think require some 3 or 4 lines of proof, and you will see it. So we need some weaker truthful notions. So I'm going to define the truthful notions, which is called risk-averse truthful. This is motivated by the I cut, you choose principle. There's some kind of truthfulness behind this I cut, you choose procedure. This is because in some scenarios, an agent does not know the valuation of the other agents. So I say a mechanism M is risk-averse truthful if either misreporting FI is non-beneficial, or there's a chance that M allocate some allocation to AI with less than proportional value. So if the agent lie, either the lying is non-beneficial or the lying would actually harm the agent significantly. So I'm just going to list the results. I propose a mechanism that is envy-free, proportional, and risk-averse truthful. And I also propose a mechanism that satisfies weaker fairness notion called proportional, risk-averse truthful, but it has a special property that each agent receives a connected interval instead of a union of multiple intervals. So I'm also briefly going to describe what I have for relaxing the fairness. So the proportionality can be naturally relaxed to alpha approximate proportionality, which is shown here. This is a natural way to relax proportionality. And the main impossibility result can be extended to the setting where the exact proportionality is relaxed to some 0.97 approximate proportionality. The proof is mostly similar, but require a lot of bound analysis. And there's some future work here. I believe it's an important future direction to study does there exist a truthful and alpha approximately proportional mechanisms. And I think this question can be asked in a general sense. Does there exist a truthful mechanism that is at least reasonable? Because most of the all the truthful mechanisms, as far as I know, are kind of very trivial ones, which allocate for example, like allocate the entire cake to a single agent, or just cut the cake evenly into n pieces and allocate them. These are kind of oblivious to each agent's value density functions. And we do not even know what a truthful, is there any at least a reasonable truthful mechanism, what a truthful mechanism can do. So I think a future direction is to understand how much can truthful compatible with the fairness. Okay, that's all. Thank you.
We have time for some questions. So, online audience can write their question on the chat.
So I have a question.
Yeah, please. Go ahead.
Sorry, unless someone in the room has a question. So my question is, your notion of risk-averse truthfulness is very strong. It's very impressive in the sense that it's basically truthful regardless of how minute or strong what risk aversion is, right? So I was wondering if you're willing to tolerate only, risk aversion, which is not super strong, but only somewhat strong. This would give you more power. If you have any thoughts about what can be achieved with that.
So I didn't copy the first part of your questions. You are saying that the risk-averse truthfulness.
I'm saying the way you define risk-averse truthfulness, you're basically truthful for any risk-averse buyer, participant, regardless of how if they're very risk averse or slightly risk averse. It's a very strong definition, which makes your mechanism very, very appealing. I was wondering if you only required that you be truthful for buyers that are a bit risk averse and not, very, very risk averse. So you could actually have things that are suboptimal, but not with very high probability. Would that give you a lot of more leeway? Have you thought about what you could do in such a situation?
Yes, if I get your question correctly, you're asking that is there a way to define the risk, some truthful notion that is stronger than the risk-averse truthfulness, but still weaker than the dominant strategy truthfulness. I roughly thought about this, but I do not have much idea. I agree that the current definition of risk-averse truthfulness is a little bit weak in the sense that it is some kind of worst-case analysis. If there's some risk that the agent, if we can construct the remaining n-1 value density function under which I would receive less, then I prefer not to lie. This worst case stuff makes the definition somehow weak. I try to think about some stronger notion, but I do not have much idea because I know there's in other area like auctions, you can assume that the other agent's valuation is drawn from some distributions, and then you can talk about some Bayesian Nash equivalent, this kind of stuff. But in the cake cutting sense, I do not see if there's a natural way to define a distribution of functions. So, I thought about this, but I do not have much progress on this.
Thank you so much. Thank you so much. The very, very interesting answer. Thank you.